Gives me pleasure to welcome you all to our webinar today on enhancing the quality and interoperability of soil data through laboratory quality control and analytical method validation. I'm sure I can never overemphasize the importance of quality control in our soil analysis work. But more importantly, to that aspect, today we are delving further to consider the issues to do with analytical method validation, which I presume is a prerequisite for judging suitability of the data that we produce as laboratories. So we've got a rich panel today to take us through this topic. We have two main speakers. Our first speaker is not a stranger to most of us. Joseph Uponi from Nigeria. He's quite an experienced laboratory specialist. He has actually worked for a very long time in managing laboratories, and he actually was the first chairman of Glossolan AFRILAB, specifically in the AFRILAB region, and he has been in the steering committee of Glossolan since for the AFRILAB region since 2019. He's also a registered soil scientist, experienced mainly in the installation, calibration of equipment, and also training in terms of preventive maintenance and many other aspects to do with laboratories, specifically soil testing laboratories. So you will be our first speaker, and we also do have another speaker who will also take us through the aspects of method validation. Her name is Noorunisha Abdool. I hope I got it correctly. So Noorunisha is sitting in South Africa. She is also quite experienced in laboratory activities, having worked um, in a number of laboratories within the environmental laboratories and other industries, and most importantly, in the agro industry, mainly in soil analysis and fertilizer analysis. She's quite active in AgriLASA, which is a grouping of laboratories in South Africa and some that are actually in the Southern Africa. And she's also quite knowledgeable in terms of ISO 5 and many other standards. And she has also successfully accredited soil testing methods in a number of laboratories in her career. And currently, she's a SANA's approved technical signatory for 12 soil and plant methodologies. So you can imagine the richness that we do have today in the panel. And to also assist to respond to some of the questions that may come through, we have Rolf. Rolf is also no stranger to us. He's a member of the Glossolan Steering Committee at the global level, and he's also quite active within the AFRILAB community. And he will also be joining the panel, and we hope to have the AFRILAB chair, Lesego, joining through. In fact, she's here with us now. And we also hope to have the Glossolan chair, Mustafa. Unfortunately, Mustafa is in the field, so he may fail to join us for this webinar, but we hope he will join later before we finish. So that is the panel that we have, and would have wanted to have some remarks to just open it from Mustafa, but now that Lesao is here, I'll kindly ask you to just give a very short opening remark before we give our first speaker the floor to take it over. Lesao, please.
Thank you very much, Bellington. Good morning or good day to everyone. I'm happy to be here again, and I believe that everybody is happy to be here. And based on the introduction of the facilitators that we have just received, I believe that everybody is looking forward to getting as much information as they can. And this can only be possible if we can all be participating. Can we appreciate what they're putting forward by debating or asking questions or making some inputs in anyhow? That way we can really benefit from what they will be sharing with us. I wish we have a very fruitful webinar, and I welcome all of you here. Thank you very much, Bellington.
Thank you so much, Lesego, and a warm welcome to you as well. At this
Thank you.
juncture, let me just remind attendees that we are recording the webinar and it will be posted on the Glossolan page as well, the GSP webpage. Very soon we'll advise you when it's posted. Again, for all the other attendees who are not part of the panel, you will not be able to provide your feedback or your inputs audibly, but you are free to use the chat for your other inputs. And if you have any questions, specific questions for the panel, please hit the question and answer tab and put your questions there. I'll be monitoring them. And at the end of the two speakers, we'll open it up for question and answer. I would want to promise you that all your questions will be addressed. So please feel free to write in your question at any point that you feel you would need to put in your question. We'll certainly capture them and bring them to the attention of the speakers. So without wasting much of your time, let me call on Joseph to start the presentation. So Joseph is specifically speaking on the quality control practices in soil laboratories in general. Joseph, please, if you can share your screen and you have the floor, please.
Thank you, Rolf. Let me share the screen. Share. Can you see my screen?
Yes, we can. So just put it in presentation mode.
Okay,
Yes,
thank you very much.
that's
Good morning, good afternoon, wherever you are. I am Joseph Uponi from International Institute of Tropical Agriculture, and I'm making this presentation on quality assurance, mostly prepared by Rolf, my colleague in the steering committee, with some minor additions by myself. I hope that at the end of the presentation, we'll be able to have a robust discussion on various aspects that have to do with quality control, either immediately after this or after the final presentation by my co-presenter. Well, we know that the world is a small place now, and there's a globalization of trade that requires that we guarantee the quality of data that we exchange. Now, in the context of agricultural development and climate change, it's very important that very important decisions are based on results that come from laboratory analysis. It's amazing because we know that the world is getting digital and everybody wants to be able to quantify whatever is being done in tangible terms. And that's why results from the lab have become very, very critical. Important to have some indication of the quality of the results, therefore, that are emanating from our labs. Project the analytical work that we do in such a way that everybody is able to accept the fact that it is credible and results. I mean, the decisions that are made from there actually give good results. We know that most of our laboratories work according to established procedures and we do not change often. We are encouraging most of us now to adopt the SOPs from Glossolan for the purpose of making sure that our results are comparable and standardized. Otherwise, some other labs are also using certified methods that are available. I think my other presenter will talk more about those methodology, validating those methodologies during her presentation. Quality work can only be performed if all materials used are suitable for the job. And properly organized for. Across of our countries, the materials which we use are not really produced in-house, but we have to import them and to maintain the quality of those materials. equipment or reagent, but in order to be able to produce the type of results that we are aspiring to have. Apart from the reagents and the tools, those of us who are performing the analysis also, the way we handle the materials go a long way. So it's very important that we have good reagents, good equipment, but we should also have good staff who are able to handle those materials. It's not only the technical aspects, such as sample preparation, but also this safeguarding of identity and integrity of samples, as well as how we dispose of the sample to make sure that we do not cause environmental pollution or environmental hazards. Quality control is the term used to describe the practical steps taken to ensure that errors in the analytical data are of a magnitude appropriate for the purpose for which the data will be put into, will be used. This implies that the errors which are unavoidably made, we know that errors exist in every system, but we should be able to know what magnitude those errors are and know what corrective actions to take when those errors are getting out of proportion. This is very, very important that somehow we're able to quantify the errors. And that way, we know when the things are getting out of control or not. The control measures must be able to detect both random and systematic errors. Random errors are not, those are inherent in every measurement that we make. But systematic errors are usually within our control. They result from the way we actually carry out the procedures. The procedures for QC primarily monitors the accuracy of the work, trying to measure the bias with the help of certified reference samples and control samples, and use of replicate analysis of the test samples. Now, the goal of this is to make sure that our analysis is actually precise and accurate. We have a little pictorial representation of what we mean when we say our analysis are precise or accurate. The illustration here is like a dartboard. Every sample has its true value. Now, when we make measurements, our measurements can be precise, in which case we have repeatable results. We're able to get the same result every time we are analyzing. So there's not much variation between the results. In that case, we'll have something like this or like this. That's high precision. But in terms of, high precision, the results are going together. In terms of accuracy, it's very, very important. It's very, very important that the results be as close as possible to the true value. Now, when you have high accuracy, on the average, you get to close to the results. Like here, if you find the average, it may end up at the target, but you can see how scattered the thing is. So this is not very good. Here, you have low accuracy, low precision, because they are scattered, and when you find the average, it still doesn't get close to the target. Our aim is to have high accuracy and high precision. And to be able to do this, several procedures have to be in place. Oftentimes, we use control samples, that is samples of known values that have been certified, to be able to see how well we are getting close to the expected values. Now, when we do those analyses, it's important for us to have control charts for every control sample that we have. Each control sample must have a control chart. And the Shewhart control chart sets limits for accepting or rejecting analysis. Usually, we have the control limits and the warning limits. The warning limits give you an indication that something is going wrong with your analysis. And usually it is set at plus or minus 2 standard deviations away from the mean, while the control limits are 3 standard deviations away from the mean. At 3 standard deviations away from the mean, you should reject the analysis altogether because it means it's too far from the expected value. Like I mentioned, all control samples must have their individual control charts, which looks something like this. You have a mean value, and you have the upper warning limit, lower warning limit, upper control limit, lower control limits that are set by those standard deviations that we have set. These values will change depending on the type of samples that you are analyzing. But this is the statistical way of making sure that your samples, your analysis is under control. Every time you get results that are less than 2 standard deviations away from your mean, you accept your results. But if it's more than that, then you begin to find out what the problem is. And certainly if it is more than 3 standard deviations, you have to repeat the analysis. There are other parameters that we use also in interpreting our control charts. For instance, if your samples are constantly above, if a set of batch of analysis begin to have results that are constantly above the mean, they may still be within the control unit, but systematically above the mean. It means somehow your mean has shifted. That means there's a systematic error which you need to go and investigate. The fact that it fell within control limit, but is now shifting to a particular side of the chart indicates that something is going wrong with the analysis. We expect that the control sample, each batch we're analyzing with the control samples, the means should be varying randomly around the mean. If it's not so, there are several steps that we need to take in order to investigate and find out whether the analysis is out of control or not. Now, the analytical methods for quality assurance with respect to instruments and other equipment, the following requirements should be met. Apparatus used for generation of data and for controlling the environment relevant to should be suitably located and appropriately be able to meet the requirement. The apparatus should be periodically inspected, cleaned, calibrated according to the standard operating procedures, and records maintained. I want to emphasize this because oftentimes we do our internal calibration of equipment and maintenance, but we need certified instrument calibrators to come and verify that our equipment are working. Let me just take, for example, the UV visible spectrophotometer. How do you know that your UV visible spectrometer is working properly? We have commercial filters that you can use to check whether your UV visible spectrophotometer is working. These filters, you put them in your sample compartment and they tell you what absorbance is expected at a specific wavelength. So when you use those filters and you are getting the required absorbance, you know that no matter where your readings are taken to, if the equipment the other people are using are okay, you should get similar readings. I dare to say that most of our labs in Africa don't have these filters with which they check on their UV visible spectrophotometers. But apart from the filters, we also have concentrations of various reagents that you can use to test the accuracy of your UV visible spectrophotometer. In the case of atomic absorption spectrophotometer, we have sensitivity checks, certain concentration of the analyte that is supposed to give you 0.2 absorbance. So when you measure those concentrations and you are getting close to that 0.2 absorbance for that particular element, you know that your AAS is operating properly. Every equipment we use in the lab have specified procedures for checking that they are working properly. And it's very important to do this periodically to be sure that your equipment are functioning well before you begin to do analysis. That means a lot of records and forms have to be in place. Actually, part of good laboratory practice is that you keep a record of all these documentations of calibration of your equipment and tools that you are using in the lab. Another critical factor is the way the samples are handled. You know that such factors as moisture content, the time lapse between sampling and analysis can affect the results that you analyze. Typically, for instance, if you want to analyze nitrate in soil, usually you want to do the analysis on fresh samples. And when those samples are collected, they're supposed to be refrigerated to be sure that there's no degeneration in the samples. Otherwise, what you are measuring is not really related to what is actually in the field. That is for that type of measurement. But for most of our routine measurements, we use air dry samples. So that may not apply for those ones. But if you have high moisture, if you have moisture content varying, you imagine, for instance, if somebody is in Niger, the atmosphere there is very dry, so the moisture content generally is a bit lower. In Nigeria, southern part, the humidity is very high. Now, that's why we always expect that samples are the results of samples are expressed on oven dry basis. So you always need to do moisture content in order to be able to get accurate results that are comparable to other places. Otherwise, just variation in moisture can lead to variation in the results that you are getting that has nothing to do with how wonderful your equipment are or not. So these are important things to take into consideration. Also, the way the samples are collected. Of course, the more samples you collect, the more representative the sample is of the true situation in the field. But there's a limit to which you can do that, and there are sampling methodologies that are already in place. We will not emphasize that too much in this instance because we are concentrating more in the lab. But once you get the wrong sample, all your effort in the lab is wasted, no matter how accurate the analysis is. So we are concerned about how the samples get to the lab, and oftentimes we have to assist our clients to make sure that they follow proper sampling and packaging and labeling procedure before the samples reach the lab, so that our efforts will not be wasted. In fact, SOPs, protocols, registration forms, and labels can be prepared for the clients. Oftentimes, we even prepare those materials and give to them just to minimize those errors. The integrity of the sample is so important so that throughout the period of the analysis, you can maintain the integrity without mixing up samples. This is all part of the good laboratory practice that's supposed to go on in the lab. It's a very terrible thing when samples are misplaced or not properly identified. You can imagine somebody bringing samples, some treated with nitrogen, others not treated with nitrogen, and then you interchange the results. The implications are far-reaching. Even though we know that the system may not be foolproof, but that which is within our control, we have to ensure that we maintain the integrity of our samples from the time they come in to the lab till the analysis are completed. The most important part of this work is, of course, the analytical procedure, meticulously performed according to corresponding SOPs. Now we are recommending the Glossoland SOPs so that our results can be comparable. For some reason, some people may use some other methods of analysis, but it will be good to be able to find out the relationship between whatever other method you are using and these standardized methods so that your results can be comparable. Relevant aspects include, in the SOPs, you find information on calibration, the use of blanks, and other performance characteristics. Well, blanks are very important because they help to take care of any background errors and other things that are not related directly to the analysis. You need to be able to analyze blanks with every batch of analysis that you are doing. It takes care. There are different types of blanks. There are reagent blanks, there are instrument blanks. All those ones try to eliminate errors that are common to all the samples. Usually these are samples that just do not contain real samples, but contain all the reagents that we use for the analysis. The whole idea is to minimize the sources of errors. It's very, very important that when we generate our QC charts, there have to be a systematic way of checking this on a day-to-day basis to be sure that whatever we are producing is reliable. That an analysis went well yesterday doesn't guarantee that it will go well today. And that's why oftentimes for the lab manager, you often include things like blind samples. Blind samples are samples that you already know the value, but the analyst doesn't know the value. You put them in every batch, and when they bring the results for analysis, you check whether the results are within control or not. Even for those blind samples, you should have a QC chart to be able to determine the limits. The duplicate analysis also help. The duplicate analysis help to address the issue of whether your analysis is precise or not. Precision, that's this ability to get the same result all the time. Your duplicate analysis must not be more than 5% different from one another. Once they are more than 5% different from one another, you need to investigate and find out why and make the necessary corrections. External quality control involves use of reference materials from other reputable laboratories. They are commercially available. We have different companies that produce those materials. Howbeit, they are very expensive. And for us, in most of the African laboratories, it is difficult to sustainably obtain those materials. But that's not a problem, because if you go to the Glossoland website, you will find how you can generate your own internal control samples using these expensive ones. That is another topic to be handled at another time. Now, these international samples are very important because they help you see on the spot whether you are getting accurate values or not. Once you are able to get accurate values, then you should generate your own internal samples, analyze it along with those international samples, and that way you have your own internal control samples. Also, participation in proficiency testing is your true proof to the whole world that you have quality analysis. We have examples of such type of proficiency tests like the WEPAL from Wageningen, BPA from France. They send samples at regular intervals, but they are expensive also, but they are necessary. There's also the third line control where you make comparisons of different parameters of analysis. You'd expect, for instance, that there's a relationship between your pH and your exchangeable acidity. When you have high pH, you don't expect much exchangeable acidity. So if you are getting contrary readings like that, you can always query and go and find out what is happening. There's also a relationship between your pH and exchangeable calcium in the soil. Even your organic carbon and total nitrogen have some relationship. When you find CN ratios that are outrageous, that are beyond 20 or below 8, then it's good to cross-check. Those are third line controls which experienced lab people can always find out after the final result has been compiled. Also, the way we report our results are important. Of course, sometimes we report to many significant figures, which is not really necessary. This slide just tells us how to round off our figures and how to know what decimal places are necessary. Oftentimes, make sure that you round up your figures at the end of your calculations. Don't round off in the middle of your calculations. This is just the procedure for determining the significant figures. In rounding up, I would like to just mention that when it comes to the issues of quality control and quality assurance in soil testing labs, 4 key things are important. Make sure that the samples have been properly collected and that the sample integrity is maintained from the time of collection to the time of analysis and disposal. Secondly, make sure that your equipment are properly calibrated and vouch for that they are performing according to expected standard. Lastly, that the people who are performing the analysis are adequately trained to be able to carry out the procedure, and that you maintain proper records, especially your quality control charts for all your control samples, so that you're able to know when analyses are out of order and then be able to take corrective measures to be able to bring the analysis back in order. That's just a brief summary of what some of the steps we need to take in order to maintain the quality. Above all, the quality must be attestable. That is, when you participate in sample exchange programs. We are grateful to Glossoland, who has provided the one that we participate on free of charge. We are not paying for that yet. I hope they will not begin to charge for that in due course. But that is our lifeline for now for most of the African labs. Otherwise, you have to participate in the international ones, make a little investment in that in order to be able to make a good statement on your quality of your analysis. Thank you for listening.
Thank you so much, Joseph. That was quite comprehensive, and thank you for highlighting the importance of having accurate and precise data in our soil testing labs. And it's quite interesting that we certainly have been seeing an improvement in the output of our laboratories in Africa, mostly from the recent PTs that have been ongoing. And we hope that improvement should continue, and especially with the tips that you shared, this should really come in handy to assist. And again, members, we are free to post questions if we have any for Joseph or any of the panel members here. We will certainly address all the questions that would be coming up. So what we'll do is we'll have the question and answer session at the very end. So if you have any questions for Joseph, feel free to type them in the question and answer section. And for now, I want to leave the floor to Noorunisha. So Noorunisha is going to pick up from where Joseph left, and she will be delving further into the issues to do with method validation, specifically for soil analysis methodologies. So Noorunisha, please, you have the floor. You can kindly share your screen and take the floor.
Good morning, everybody. Good morning, good afternoon, good evening to all of the participants as well. Thank you, Bellington and Joseph, for that lovely introduction and some really good tips on how do we actually need to have accurate results. So this morning, I'm going to talk you through method validation for soil testing. I'm going to try not to bore you to death with statistics. We're going to look at some of the parameters that we have to include in a method validation, how we actually go about determining those parameters, and then obviously the biggest one, you have a set of numbers, how do we interpret that, and what is its implications to ourselves, to our laboratories, and to our clients. Okay, so analytical method validation. I'm going to try and make this a little bit less of a mystical, magical topic that only wizards and witches can do, and I'm going to try and turn it into a little more science. The first place that we're going to start is we're going to go to our ISO 17025. This is the only document that I reference in this presentation that actually has a cost attached to it. The rest of the documents will have a reference at the end, and they are free and you can go and download them. Okay. So what does ISO 17025 say about validation? It's where specified requirements are adequate for intended use. That is what it says. So what does that mean to us in English? In order to verify something, according to ISO 17025, the provision of an objective evidence that given items fulfill a specified requirement. What that actually means. Method validation is a process where the laboratory proves their method is fit for purpose. And the fit for purpose is where this actually comes in. So we don't want to be analyzing organic matter in soils, for instance, and we're reporting high values when our client is actually looking for low values in a sample that has no organic material. So fit for purpose not only takes into account our client requests or our client requirements, it also takes into the account the abilities that the laboratory has. Some laboratories, like Joseph has said, our European counterparts have a lot of funds and often are affiliated with research institutes. So they have expensive instrumentation or the option to use expensive instrumentation, where a lot of our startup labs in Africa are not necessarily exposed to this. So when we set up our method validation, is the method that we're using, is the instrumentation available to us? Is it actually what the laboratory can do? Does that mean it helps our client? And most important, what does that cost for both the client and the laboratory? So a method validation is going to include all of your performance characteristics for your analytical requirement. And that's quite a mouthful. Your analytical requirement is what your laboratory or what your client is going to tell you. So first we start off, where should we actually start and why should we validate the method, right? It's not going to be a few days before your audit day is scheduled to arrive. That is not when it's going to happen. Okay, Joseph has touched on a few of these topics. He was talking about control charts. When your control charts show you that your sample is drifting, that your mean is no longer where it used to be, that you're getting closer to your 2S or you've reached your 3S limits already, do a method validation to ensure that your method is still fit for the purpose. If you have a new method that you are busy developing, if it's in-house, do your method validation. If you need to take a method that you already offer and you are then going to update it to accommodate new customer requirements, you have to have a validation. Here it says laboratory QC shows the method is changing with time, which is exactly what Joseph touched upon. If your mean is drifting or you are touching your 2S or your 3S on your control charts, you have to do this. Method validation is also a requirement if you are going to be ISO 17025 accredited. And then most important, if you are moving your instruments, if you have changed the environment or you've gotten new instruments, a lot of ICPs, for instance, you can take the software and the method on your ICP 1 and transfer it to your next one. Your two instruments are not actually the same, so you're going to have to do a method validation there. There are big method validations and there's little ones, and I'm going to take you through all of them. Okay, so my first question was, what does your client need? So your client wants organic materials in soils, or they want calciums in their soils, or they want their nitrogen content in their soils, or as simple as they want the pH of their soils. That is how you're going to set your analytical requirement. You either have a new method or you have a method that's existing already, and we work from there. Is your laboratory able to offer what your client requires? You're not going to give him a pH method if he is looking for a phosphorus spray, for instance. Okay, we're going to do our method validation and we are going to determine if the results we get and the parameters and the boundaries with which that method happens is actually what we expect. And then the big question, is it fit for purpose? If the results we get fit within those boundaries, then yes, your method validation is fit for purpose. You issue your validation report and you can use your method. That sounds really easy. So I'm going to talk you through all of these steps. And a lot of you now may be asking yourself, well, where do we start? Get yourself some documents. You have the ISO 17025, which I have said comes at a cost. You can get your TR26, and I'll show you where to download this in a moment. Your laboratory will have a validation plan, and you should already have an internal quality management system. So your internal quality management system is what Joseph has touched upon as well. Your calibration records, your repair records, your maintenance records, all of those become part of your management system. Then, of course, you're going to need soil samples. Now, we touched on this a little bit where we use internal soil controls, or we have CRMs, or we have PT samples. I have a little star against internal soil controls because you can't just have a soil, mix it up and use it. You need to have a control that is stable. And Bellington has shared where you can actually learn how to make your soil control samples. So that's going to be quite a helpful document. Some of the PT suppliers, and this is not a comprehensive list, this is not even the tip of the iceberg. You have ALP in the States, you have AgriLasa here in Southern Africa, and of course we have Glossaland. And when it comes to reference materials, these do not come cheap, but they are a necessary requirement in your laboratories. You can use the agromats. You get an agromat 1, 2, and you get a CP1 as well. So that's a compost sample. These are nice because they have different soil types. So you'll have a sandy soil, a compost soil, a clay soil. You can also get synthetic soils with different analyte contents from Alpha Resources. And before you used to be able to get a Sigma Aldrich Montana soil, I'm not entirely sure if those are still available, but we can look up them if you need them. Okay, so we get to TR26. You go to the SANAS website, www.sanas.co.za, go to publications, and you are going to see documents. Type in TR26, and you are going to see the document that's on screen. You can simply download that, and you will then be able to follow the document I am now going to speak through. So in TR26, it gives you the purpose of the document, and it breaks down the ISO 17025 requirements for method validation. Very important, it does not do anything, it does not handle sampling or sample handling and transportation. That is, a lot of laboratories do not do that. It's not a service that is offered. But if you do offer it, that is something that has to be handled outside of your validation. Okay, so we're going to go through some references, definitions. We're going to define each of the performance characteristics that we have. We're going to set up a validation plan, and then we're going to review its implementation. Finally, we're going to have a summary report and decide whether or not we're going to have to revalidate. So what is a validation plan? Well, basically, that's your blueprint. Going to ask a lot of questions. What analytes are you doing? Why are you doing them? What kind of matrices do you have? Are there any interferences with the analytes you're looking at versus the analytes that are also in the sample? Then we're also going to look at the different characteristics that you get. And these names are going to come up quite a lot. It's going to be accuracy, bias, precision, reproducibility, linearity, working range, limit of detection, limit of quantification, sensitivity, specificity, uncertainty of measurement, and robustness. Some of these might sound foreign, some of them you may have heard of already. They sound really scary, but actually I'm going to show you how to do this in a fairly easy manner. What I wanted to do was break down some of these performance characteristics a little bit, and what do they actually mean? So you'll see this coming up in the next few slides over and over. So we're going to start with identification. Basically, what is identification? It is what are we measuring and how are we measuring it? Okay, so ideally we need to know what instrument we're using. I have referred to if you have multiple ICPs, you can't just say that you are validating your method for cations in soils on your ICP. When the auditor walks in, they're going to ask you, well, which ICP are you using? You have to have each of your instruments uniquely identified. In my previous life, I did some work for one of the laboratories in a pharmaceutical world. They were all females in that particular department, and they named all of their instruments against Marvel superheroes. So their ICPs were Spider-Man and Iron Man, and I think there was a Catwoman as well. So I thought that was quite clever. And it's an easy way for everyone to identify exactly what you're talking about. If you've got 6 instruments that are all the same, give them a unique number somewhere along the line. Okay. We also have to an extent, identify the interferences that could be caused. So you can list all of these in your method validation plan that you suspect they will cause interference. But when we get to selectivity, you are going to then see how we determine this as well. Okay, accuracy. Joseph gave us a lovely definition of accuracy earlier, and it's basically how close is the measured value to the true value. The true value is, of course, the one that we are using our CRM for, or our PT sample, or our internal control sample. It is the known value of the analyte in the soil matrix that we are working with. There are 4 ways to determine accuracy. Spiked recovery tests, which are really difficult in soil. You can't always spike a soil sample to do a combustion carbon, because how are you ensuring that your analyte is homogeneous and evenly distributed? You can do alternative method testing, but it's always going to lead to more questions than answers. And then obviously you have your proficiency testing and your certified reference materials. Prize 1 is always going to be your certified reference materials. If you cannot get them or you cannot afford them, use your PT sample. Okay. So how do you do accuracy? You run that test, or you run that method for 10 different times. Ideally 10. You can use less if you press for time or you don't have much sample, but it's not always ideal. Please don't run it for 1 or 2, because 2 is not an average. A minimum of 6 is usually where we draw the line. There's many ways to report your accuracy. I prefer always using Microsoft an Excel sheet. That's simply because it will calculate a lot of things for you. You can put in formulas. But if your laboratory has a validation template, please use that as well. And yes, you use your certified reference materials. Your consensus value will be your true value, which comes off of the certificate. If you're using a PT sample, the consensus value will be the one reported by that scheme. Okay, this is going to look very similar to what Joseph did, but accuracy also includes precision and trueness. So precision is how similar the tests are when compared to the result of the CRM, and trueness, how close is the mean to that CRM value. So you're going to recognize these from Joseph's slide. No, we did not share one another's, but you will see in the left-hand side, of my left-hand side, you have a very close clump of blue dots. So we have great precision, but we're very far off from that center dartboard. So we have very low trueness. On the alternate, you can have high trueness, and we have a big group of samples sitting in the middle circle, but we have just as many, if not more, sitting on the outside circle. So high trueness, low precision. What we're really looking for is all of the blue dots in the center circle all together with very few outliers. So that is how we're going to determine our accuracy. Now, you can also use accuracy to determine your bias. What is your bias? It is the systematic error of measurement. That means it's not you, it's not your colleague, it's not your glassware, it's not how you extract your soils. It's the inherent error within your system or your equipment. So how do we deal with this? You can have high precision and high bias. You will see they're 2 very separate entities. You can have low precision and high bias. You can have low precision and low bias. And you can have high precision and low bias. That's obviously the one that we want the best. We want to know that our system is actually reading the true value of that analyte. Okay, again, you run this and you can calculate this when you are doing your accuracy. So on our list of performance characteristics, we've now done 3 characteristics with 1 set of analysis. Moving on to linearity. Linearity is a mouthful of a word that basically tells you how well does your method read your result across a range. So we start at 1 or 2 ppm. Can we go up to 10 ppm? Can we go up to 30 ppm before those results start flatlining? Okay, so 99% of the time it's going to be a linear calibration, and it's going to look like this graph. This is an example of carbons in soils determined by Walkley Black. And ideally, we usually accept a concentration analyte range of between 80 and 120%. You can also then work out your working range from your linearity. So you'll see on the bottom graph, that is a linearity from an ICP. You'll see that they look very different from one another. The one was done manually from a titration for carbon in soils, and the other one taken straight off the ICP software. Okay, what we want to eventually see is you will see in the second graph that it tapers off slightly and it starts flatlining towards the top. That's what we know. It needs to stay linear. So before it starts flatlining, that's where we're going to cut off our working range and say, we are 100% accurate and sure of the result we are giving you between the range of 0 to 100 ppm for the particular analyte that we're talking about. So what is your working range? I hope I've given you a fair enough explanation, but your working range is what is the valid range for that result. We're obviously not going to go from 0 to 100%. We just want a certain concentration. So you'll see at the bottom there, I made a note, CRMs are not always widely available. So in AgriMat 1 and 2, for instance, you get quite a number of analytes that they have determined, but you also may not get certain analytes that you are looking for specifically. So if you are participating in a PT scheme, especially one that is based in your region or covers your region in terms of soil specifically, you will then be able to more than likely use your PT samples to do your working range because it accounts for the analyte and the method that you are looking for. Okay, good. We're going to move on to LOD and LOQ. So LOD, limit of detection, it is the lowest concentration, so the very bottom of your working range. Limit of quantification means the lowest concentration of an analyte that can be consistently measured. Your detection limit by statistics is usually calculated as 3 times your standard deviation, and your quantification limit is 3 times your limit of detection. If you are using different matrices, in soils, you can use your sandy soils versus your clay soils. In your ICP, for instance, it's not always a different matrix, but if you were in the water world, you would then have your different drinking waters or your different irrigation waters. Those would be considered different matrices. Okay, so limit of detection, basically this comes out of your ICP. This example that I'm using is your signal to noise ratio. So S for signal, N for noise. And you are looking at the lowest amount that can be distinguished from a blank. So all of these lines that you see here would be your noise or your blank sample. And then the peak that we're looking at is actually then where our LOD is. Okay, limit of quantification, we basically take that signal to noise ratio and we multiply it by 10 to give us our LOQ. The easiest way to determine this is usually your blank samples. And if you are not working on an ICP and let's say you're doing titrations, for instance, you can do your LOD and your LOQ with your working range. Okay, now the big one, how do we calculate our standard deviation? Well, it's quite easy if you use Excel, and I'll give you some tips and cheats on what formulas we can use where. This is one I had done for cations, as you can see, and I used AgriMat 2. So this is on an Excel sheet. I've literally just taken my Excel sheet and shared it here with you today. So you will see I do different sets of samples, different weeks. These are averages of samples. So I've done 10 in week 1, 10 in week 2, 10 in week 3. I then calculate their average and I put them there. This is just a small example of the samples you don't do I prefer doing 10 or more, but it also depends on the costs and availability that's going to influence the laboratory. What we're going to do is we're going to calculate the average. So we're going to calculate it individually for each analyte. One for potassium, one for sodium, one for calcium, one for magnesium, one for sulfur. If you're doing a milling extraction, for instance, you are then going to do all of the analytes that are available in your milling extraction. Going to calculate your standard deviation, SD, your RSD, percentage relative standard deviation, true value, the known value of my CRM from AgriMat 2, and your 3S is then your 3SD, which I'm going to show you how to calculate. These values that you see here in the blue block also come from my CRM. Now, here's what my CRM certificate looks like. It's just 2 pages out of a very long 4-page document. It's going to show you what sample it was, the matrix that it is, what its catalog is, and when it expires. This is very important, especially when you go for an audit. Your auditor is going to ask you all of this information. They're going to ask you to have a look at the certificate. So make sure you have both a hard copy and an electronic copy available for them. And then obviously very important, does this actually pass? This gives you a mass amount of information. You'll see that they've done different extracts here on these samples. So I'm going to talk you through it. The bit that we're looking for the most, because we're looking at cations in this example, potassium, calcium, magnesium, sodium, they do not do sulfur in an ammonium acetate extract. And you'll see the highlighted lines that are sort of a pale yellow color is what we're going to look at for potassium, for calcium, magnesium, sodium. We're looking at the consensus value. So that's the true value we're looking for. The uncertainty that is attached to that value. And I'm going to define these. So what is your confidence interval? According to the COA from the CRM, that means that your confidence level is the smaller of the bands. Your tolerance level is the larger of the bands. And it says to you, if your results are within your confidence interval, your method is working properly. If it's outside of confidence, but inside of tolerance, you may need improvement. So this is why we're doing a method validation, so that we can tweak that a little bit. And if it's outside of tolerance, then like Joseph says, you have an issue and you cannot be certain of the results that you're reporting any longer. You then have to halt your results. You cannot report to your clients any longer. Fix your method, do a method validation, adjust it, and then make sure your sample values fall within one of these. Okay, so how do we do this? This will be available, so you don't have to scribble all of this down right now as I go through it. But you are then going to look for your average. So I've given you the Excel formulas there as well. You're just going to type in is equal to average and the column or the band of data that you're looking for. Standard deviation has their formula there as well. And then percentage RSD, you are then going to calculate it in that manner. Your true value will then become your consensus value. So this is the value here that I'm highlighting at the moment. This comes straight off of the certificate. Your 3S, I have calculated. So you'll see there how I've calculated it. I've taken my LOD value and multiplied it. I mean, my true value and multiplied it by 3. Your max limit is your upper value of the tolerance value, and your minimum is the lower of that tolerance. So that is my 3S, my biggest bands. And then I have the lower limits, upper, lower, and defined concentration. That comes from your confidence interval. Once you've set all of this up, you're going to have a chart that looks like this, very similar to what Joseph showed you earlier. You're going to have your upper bands where if you are out, then you'll see we were out there. I did that on purpose where I didn't extract the soil correctly, just so that I can have this point on this chart for explanation purposes. But you will see that everything runs outside of that confidence band, but not outside of the tolerance except for that point of, oh, apologies. There we go, outside of this one here, which means that my method is working but does need some improvement. So we can then look at the different parameters that are part of the method and how we can improve it. Or perhaps there's something, your extraction, your temperature, your soil mass, your reagent is giving you an issue, and that's where this is coming from. Okay. So now we've successfully done LOD, LOQ, linearity, and working range with essentially one set of data as well. Now we're going to move on to sensitivity. So with sensitivity does your method still give you an accurate enough result if we make small changes to the concentration of the analyte? And with specificity, can you still pick up the analyte you're looking for? So if I'm looking for calcium in my soils, can I still find calcium when there's an awful lot of sodium in my soil, on an ICP? So sensitivity can be determined from your working range as well. So there's not always a need to do another set of analysis, but sometimes there is. And this is the trick about method validation. I can't give you a document that goes, this is how you do your method validation, you never deviate from it. You need to have, I want to say, a feeling for what it is you are doing. It's almost like baking. I know my mom has been trying to get me to bake, and I reckon I'm a pretty terrible baker because the method says, or the recipe says to me, add 250 grams of flour. And when I've mixed it all up, it's a bit wet. And then you get told, add a little bit of flour until the dough looks a little bit stiff. And for the scientist in me, a little bit of flour and a little bit stiff is very vague, and I'm not sure what I'm doing anymore. And that's something we have to get used to in method validation. Sometimes it's a straight up as simple titration. Here's your values. Carbon Walkley blacks have been validated. Or it could be an ICP method where your matrices are different. You've got massive interferences. Your one ICP has no issues at all with interferences. The one right next door to it does have massive interferences. So it's also about understanding and interpreting what you are seeing and how to account and adjust for that. Okay, slightly off the topic. For sensitivity, we are going to then change the concentration slightly. So I'm not going to look necessarily at a concentration of, in this example, a 2% organic matter, and then see if the method's sensitive by going to get a 10% organic matter. We need to have them as close as possible. In this particular instance, I did not have CRMs to do this exercise. I used previous PT samples. So these samples were about a year old already. They are sealed, they kept in a closed cupboard, nothing interferes with them. I go get their old reports and I say, okay, these are the values that we were looking at. I will then use these specific samples. You'll see that on my top table, my sample was SMP 2403. That was a PT sample. And I was fortunate enough that Agromat had one that was close to 0.29 at 2.6. So I used those to determine my sensitivity. And like I say, if you are doing ICP, for instance, you have to do this for every single analyte. So in the case of cations, it's all 5 of them, not just one of them. Okay, specificity. Ideally, a CRM that represents your sample matrix or a PT sample that represents your sample matrix. You don't want to be doing a compost sample when you are doing normal soil analysis for clients and farmers around your laboratory. The way we normally show specificity is you spike your samples with different concentrations. Again, not so easy when you are doing a dry soil. You can spike your liquid samples, that's much easier. So like I say, spiking is not always possible. Something like carbon in soils is going to be an issue. To show my method validation and specificity for this particular example, I use the 2 different CRMs. You'll see AG1 and AG2 represent sandy soils and clay soils. So those were different matrices. Okay, now robustness. Robustness takes a little bit of imagination and a little bit of thinking as to what could possibly go wrong, because we'd all like to believe our laboratories are these perfect situations where the electricity is not going to go and the temperature is going to stay constant and the humidity will stay constant and my analysts are all having good days every day, so they're not going to take any shortcuts and not verify my balance and all these things. But the reality is that that is actually what happens. So a little bit of outside the box thinking, you show your method is robust by changing small little things that are variables in your laboratory. It could be using single analysts or multiple analysts, multiple instruments or single instruments, and everything that would happen in a normal day. So a quick idea of what your robustness could be used, what you change your temperatures. If you have to extract your sample at 60 degrees, extract it at 30 degrees and extract it at 80 degrees, see if you get the same results. Your reagent supplies, and it's not just your reagent that's made up, it's where they come from as well. They could change if you change suppliers. Your dilutions are something that can change as well. If I'm having a bad day and I've got 200 samples in front of me and I'm pipetting them individually, am I going to take a shortcut here or there? And then the same goes with weighing. Am I going to weigh them quickly, or am I going to be nice and precise? On an ICP, for instance, things that you could change, slight increments, your plasma stability, how you do your injection into your ICP, your flow rate, and your sample stability. All of us load our ICPs and we go home and let the ICP read overnight. In winter, your ICP room, is it affected by temperature or not? Are your samples stable for the 12 hours that you are there? Okay, the easiest way to determine your robustness is that control sample that we all learned from Glossaland how to actually make. Run that sample over and over and over again, at least once a day, at least 2 or 3 times a week. And then gather all of this data so that you can interpret it at a later stage. Okay, moving on to reproducibility. So this is a case of, are we able to get the same result or a similar result within reason time and time again? That means if I do it today, is Joseph able to do it tomorrow, and is Ralph able to do it the next week? So we do this with changing conditions as well. We show that locations does not mean laboratory here in Johannesburg and a laboratory down in Cape Town. It means a different location within that laboratory. Your different operators, so you want to have more than one analyst do this work so that you make sure each person is doing it correctly. And then obviously your different instruments. And then you do replicate measurements over different days on same instruments and on different instruments. So if you have 6 ICPs, some laboratories are in that fortunate position, do them all on the same one. Okay, use your proficiency samples to do this reproducibility. So something I want to point out, when you're doing your method validation, and I hope it's become clear already, you don't necessarily have to use only your agromat or your CRM sample for everything. You're going to go through that bottle very quickly, and it's going to cost you an absolute fortune. So have your CRM, have your control sample, have your PT sample. When you set your validation plan, have all of this ready. Your validation plan can be done before any of your things are, any of your soils are even purchased. So understand what it is you are trying to show, understand what it is you have available to you and how long it's going to take. Sometimes if your CRM is out of stock from a local supplier, it could take 6 to 8 weeks to get to you. So plan it nicely, understand what it is you got to do. And most laboratories still have work to get through during a day. So you have to slot this in with your normal work. You can't stop an ICP to determine this. Okay, with reproducibility, why do we do it? Because if I do it once, it's just a fluke. If I can do it 20 times on 20 different days, then I know I'm onto something and it is actually a true result. Okay, and then repeatability. So repeatability and reproducibility hold hands all the time. Repeatability is, can I get the same result or result within reason over and over and over again? So we don't change our locations, we don't change our operators, we don't change our instruments, and we do replicate measures with the same person, the same balance, the same micropipette, the same ICP on the same day. And we do at least 10 of these. Okay. And then, ladies and gentlemen, we are very nearly done with our method validation. And now we're left with the big brother of validation. I could talk to you about measurement uncertainty for a year. We would have to have an entire session on how to do method uncertainty, or measurement uncertainty rather. Maybe that's something you can look at, Bellington, for your next one. There are so many ways to do uncertainty of measurements. There are so many factors to take into account. I'm going to show you 4 ways to do it, and the one I prefer most and why. And like I say, be open to the fact that this may not always work for your laboratory. You have to do this according to the method that you are working with. So measurement of uncertainty is basically how far from that true value can I be within a range. Why would we want a measurement of uncertainty? It has to be reported to your client if they request it. So normally on a report you will get from your laboratory, it doesn't give you a value. It will say organic material 3.45%, and it doesn't say plus or minus 0.22% at the end. That 0.22% at the end is actually your uncertainty of measurement, that if your client requests it, you have to report it. You cannot report a measurement of uncertainty if you haven't done a method validation. And then, of course, if you are fortunate enough to be going for accreditation for your method, you have to have an uncertainty of measurement there. Okay. Also bear in mind, I myself still do get caught out with this sometimes. Uncertainty is with your result. It's not with your method. Your method is not uncertain. It is the result that has a range that is uncertain. Okay. How do we do it? Well, you can do it either as a single laboratory and you can then use your ISO GUM, or you can use a statistical approach. I prefer the statistical approach. I'm a stats girl and I love my Excel spreadsheet, so this is how I do it. Or you can do it intra-laboratory. They will then either have a PT scheme for you. Often, if your PT scheme is part of ISO 17043, they will the part of their accreditation is actually the uncertainty that you have to do. And then, of course, you can do a statistical approach, ISO 5725, which also deals with inter-laboratory measurement uncertainty. So here's how we do the statistical approach. And this is going to sound really simple, so I hope it gives you all a giggle. You take your analyte that you are determining, you get 3 operators, 3 mass balances, 3 instruments, and multiple days. You do all of your analysis over, let's say, 7 days. We get 90 test results. You work out your mean, you work out your standard deviation, you work out your expanded uncertainty, which is normally your standard deviation multiplied by 2, and then we report it. I'm pretty sure Ralph and Joseph will agree with me that is not as simple as it sounds. But that's the basis of your measurement uncertainty. You are then going to report to your client your test result, whatever that may be. In this example, 75.42% plus or minus 0.22%. You have to put the K equals 2 there. That shows you have a 95% confidence interval. Okay, how do we go about this? So there's the idea to calculate uncertainty is every possible thing that you use. So your CRM, your glassware, your pipettes, your volumes of water, your reagents that you use, your glassware, your temperatures sometimes to an extent. Every single one of those has their own built-in little inherent error. We need to take all of those errors, add them all up, and then say, for us to use method A with all of these uncertainties built into it gives us an expanded uncertainty at the end. So I'm going to talk you through a few of these steps now. If you are using a CRM, you're going to have your analyte condition, and the values that you see there are going to come out of your COA. So you don't have to go do this. Get your COA and use these values. It's going to tell you all of the information you see on the screen on your certificate from those CRMs. Then in this particular instance, I had different balances. So I weighed out PT samples on one balance, and I weighed out water on another balance. And you will see that I did them at different masses, so 0.5 gram and a 20 gram. And then I calculated my average, my standard deviation, and my expanded uncertainty. This is an example of the different reagents and chemicals that we use. This is a walkie black titration, as you will see. And also it was done using any of the dispensers or micropipettes that I used in the method as part of my equipment. So you're going to do it 10 times. You're going to list everything. So my dispenser for the first one you will see is for sulfuric acid. It used dispenser 4. And it was for 20 grams, and that is how I set it up. I just have to move slightly. Okay, so then I did the mass or the mass of sulfuric acid. Obviously, your sulfuric acid is going to have a COA when it comes from your supplier as well. So you'll be able to work out your mass and volumes from your density if you are using liquids in this instance. And then obviously calculate average and standard deviation. So this is a very small, very simplistic example of your measurement uncertainty. You are going to have a table like this at the end of the day. All of these calculations are available to you, so it's not something you have to figure out for yourself. They are easily available online. Also, you're going to list everything that you then tested for measurement uncertainty, any type of instrument name that you had, the value that that one actually gave you, that value is the average you kept on calculating, and then obviously your standard uncertainty that you calculated. This table looks a bit blank because from regression uncertainty till intermediate precision, there was not many factors that contributed to my uncertainty. And in one of the ISO documents, if there's I just need to I stand corrected if it's less than 5% contribution. In the column, you see percentage contribution. You don't have to then include it into your uncertainty. So you will see in this particular example, it was calculated. The block you see highlighted here where it says expanded uncertainty 0.45 is what we calculated. And in my method validation, I am going to have this statement. Percentage relative expanded uncertainty with K equals 2 will be reported, where K equals 2 is a 95% confidence limit. And then on my reports to clients or internal places, test result value plus or minus that expanded uncertainty that you got out of your table, your units, and what your analyte is. So to give you a better idea, this is just a very simple example out of an ICP. We had all of the compounds that were looked at, all of the CRMs that we used, which suppliers they came from, what they were certified for. So this is obviously off their COAs. And then this is more information where we then calculated the uncertainty from that. Okay. And so we have now almost covered every topic in our TR26. And I take you back to your TR26 because you have to have all of the characteristics out of TR26 have to form part of your method validation in order for you to be able to comply to 17025. So the very last thing we have is our summary report. Now, there's quite a few ways to do a summary report as well. I'm going to talk you through it. But before we get there, I'm going to touch on a few things that Joseph mentioned in his presentation. In order for you to have your method validation, it's very important that you have these documents as well, or these processes involved. Traceability means, do you have your COAs? Can your suppliers supply you with COAs? And that's not just for your CRMs, for your reagents. With your water in your laboratory, do you check that all the time? Have you checked the pH? Have you checked the EC? Is it interfering with the actual analysis that you're doing? Do you participate in PT schemes? If you do, keep the samples, keep the reports, keep track of what it is you reported into your PT scheme so that you always have that. Should an auditor ask, number one. Number two, it's always good to have this information because if a method starts drifting or your QC shows that your results are drifting, you can go back with all of this documentation and data and start pinpointing exactly when there was a drift. Then you can decide what changed in your environment that caused that drift. Okay, Joseph extensively went through equipment calibration and maintenance. Thank you, Joseph. I do not have to discuss it again. But keep all of your maintenance records, keep all of your calibration records. They are, whether you calibrate once a day or you calibrate once a week, write it down, even if it's just a logbook that you make a note of these things. Put it on Excel, my favorite, and then it's stored forever and you have trace of this. Documented procedures. Your method is obviously a very important procedure. Once you have completed your method validation and it has been accepted, you have to have your method validation in your method as well. So your method has to go under review. If you have a maintenance procedure, if you have a calibration procedure, your quality manual will lead you to what kind of documented procedures you require. And then obviously, if you are not 17025 accredited, you're not going to get auditors come, but that doesn't stop the laboratory from having their internal audits. SANAS uses a set of documents for their audits. They are available to you. Go to the SANAS website and get them, work through them, and have your own mini internal audits amongst your departments or amongst your colleagues, so that we can pick up our accuracy or our quality faults a lot faster. And that means that we give our clients a lot better service. Okay, so final stretch, validation report. Many ways to do it. Your laboratory might have a template. If they have a template, use it. You can't not use it. You can set up a report in a Word document. You can set up your own validation template. And of course, because I'm the stats girl, I love my Excel workbook. So my entire report is built into an Excel workbook. And I'm going to show you how mine looks. This is fictitious, so please, these are not legitimate results from a laboratory. Everything you see is fictitious data. So you're going to start off with your cover page. Your cover page has to have your laboratory name on it. It has to have a statement that says this is a validation report. It has to have a document control number on it. So you will see mine's here says document number at the corner. It has to have the name of the method. You don't want to have a validation report and it doesn't tell you what the validation report is. You could have 5 or 6 methods in your laboratory. All of them should be validated. Each one of them has their own report. Okay. And then, of course, the person preparing the document, if there's 5 or 6 of you in a lab, perhaps only one person put together this report in Excel or in Word or on a template, have that person's name there, have the date there, and have them sign it as well. Okay, cool. So your very first one's obviously going to be a table of contents. You need to then be able to just decide if your auditor only wants to see you proving your intermediate precision, you can instantly go to your table of contents, find the page, and take them to that. A very important thing that you must have is your validation plan, which we spoke about earlier, and any of the formulas that you use. So I'm going to show you how to do that in a minute. You'll have a method summary, so you don't need to put your entire method. Sometimes it's very cumbersome. A lot of us have one-page SOPs. You can put that there. But basically, if it's, let's say, my favorite topic, carbon in soils, you are then just going to have that section summarizing, this is how we do it. It's one paragraph, maybe 100 words, and you're good to go. A validation summary, this is just on the 3rd page usually. It'll tell you all of the performance characteristics that we listed in our validation plan and what those results, what our criteria was, what is it that we had to actually meet, and what were our results for that. Okay, so validation plan and formulas, I combine mine like this. I list all of the characteristics on the one column. I tell the, in my report, how do I actually determine it? So for LOD, for instance, I had a set of standards, and this is what I did with my standards, and this is how I calculated it. If there was a calculation that I used in that particular determination, I put that calculation in there, and then I explain what that actually means. So the result that I got that's in my validation summary, how did I get to that number? Put a small explanation here. Sometimes, and I have been through many audits as well, and I'll be very honest with you, there's still days where I get nervous. And an auditor will ask you a question, and you know it, you knew it 10 minutes before the audit started, and they'll ask you something and you go totally blank. Don't panic. You've got your method summary here. You've got your method validation document. If all of your information is captured here beforehand, you're just able to read it to the auditor, and then you will be good to go. Also, if I've done this validation and I have retired to the Bahamas, the person who's going to replace me can understand what it is I did, when it is I did it, how I did it, and what I used to do it from a single document that she can look at. Okay, so this then is going to take it all across: LOD, LOQ, linearity, sensitivity, accuracy, bias, precision, reproducibility, repeatability, working range, specificity, ruggedness, and uncertainty of measurement. These all the characteristics the TR26 says that we have to account for. Then I've just given you one example because this gets really long and tedious as a working document. But in Excel, I put down my raw data that I do. I use ANOVA to determine my my F factors and my crit factors, and then I show the graph. So remember, this is for linearity. I want to show that my method is proportional to my analyte concentration. So I have all of those values and I plot them here with an R squared. Okay, if you have a method validation that you are doing on cations or milling, for instance, on an ICP, each tab is going to have all of the data that you have generated in a summarized form, and you have to have a statement of purpose. So at the bottom of this, I'm going to say my method is linear because I'm telling you I have tried to determine this. I have successfully shown that my method is linear. Just a small conclusion that says this method shows that it is linear. Okay. If you are doing milling, for instance, if you're looking for 10 analytes, you're going to do this for each and every analyte. This is not a summary one. And then lastly, you're going to have these tabs. So they're all going to look like the previous one that I showed you. You're going to show your regression for each analyte determined. You're going to show your working range, your reproducibility, your intermediate precision, your robustness, and then you are going to show how you calculated your uncertainty for each of them. So if you had your reference materials, your mass and volume, your glassware, you're going to put all of that there. Method uncertainty, like the rest of it, is all per analyte, so we have to do it over and over. The most important thing in your validation report, and I learned this the hard way, have your statement of purpose. Remember at the beginning, we said, what is the purpose of this method validation? To prove that the method is fit for purpose. So at the end of this document, have your statement, this method is fit for purpose. At the beginning of our validation plan, we said we're doing this method validation to prove that we're wanting to show organic matter in soils over a specific concentration. So this is a nice bit that brings everything together. It's 5 words. This method is fit for purpose. Okay. And then we are done with the big boy, method of uncertainty, and you will see that we've worked through every characteristic that the TR26 says we have to have for our method validation. These are the references that I used for this presentation. This presentation will be available. I have put a lot of gimmicks into it. So I have said to Bellington, I will create a PDF as well, should you need it. What you see on the screen is freely available to anybody. Go Google them. The only thing that you have to pay for is your ISO 17025. And ladies and gentlemen, I hope you've learned something today, but congratulations, you have finally done a virtual method validation. And those are my contact details. If anyone needs any questions, you can get hold of me on WhatsApp or my email. They are also on the invite. And thank you for your time and listening to me.
Thank you very much, Noorunisha. That was quite comprehensive, quite interesting, and indeed, I think it really was worth the while. And thank you also very much for keeping to time. We indeed still have quite a couple of minutes for questions and answers. So I gathered a few here that I would want maybe to pose and then you can respond. But just to mention that I think it's quite interesting, especially the measurement uncertainty part. I liked your statistical approach of just bringing it together quite easily. You know, the gamma approach is quite difficult and in so I really liked how you put it.
If you're brave.
Yeah, but yeah, I really think through the leadership of Leseko and the team, I think we should organize another separate session specifically just for measurement uncertainty so that you really go in depth into it. So I think I'll pose 3 questions and then you can respond and probably I'll do another round after that. So the first question is on sensitivity and robustness. If you can just explain more, the member really wants to understand if there is any difference between the two, and if there is, maybe if you can expand more on what sensitivity is and what robustness is. Then the second question, I think you touched on it at almost at the very end, but the question is on regression uncertainty. One of the components on your uncertainty budget was regression uncertainty. So the question is, what is it? I think you explained that the uncertainty components from the volumes for PET, and then there was that one that was a bit huge on regression uncertainty. What is that? And then the third question is the common sources of uncertainty. I think you touched this partly, but the uh, uh, question really reads, what are the common sources of uncertainty in soil testing that we should look out for? Maybe if you could give examples for certain parameters. I think you were giving examples, especially for ICP and some for May 3, but the common source of uncertainty that really contributes more. I liked when you concluded that part. I think you talked about those who contribute more than 5% are quite critical. I think that is where the question really is, the ones that we should really be checking out for. I think if you can respond to those three, as I gather more, we can then have another round of questions.
Okay. I'll address the last one first and I'll go bottoms up if you don't mind. Uncertainty, you're really looking for absolutely anything that is used in the method. So if you use 5 balances, you need to have the uncertainty for each of those 5. If you have glassware, if you have reagents that are made, so if you're making up reagents in separate glassware, then you will use that glassware. On your glassware, there will usually be a reference to the volume difference or temperature difference. And often you can also request that from the supplier of your glassware or the manufacturer. So basically, it's anything that is used in that method except for you as a person. Your CRM or your PT scheme sample, pipettes, mass balances, glassware, temperature. Sometimes methods have to work at specific temperatures. So how do you record that temperature? You would then have to use a thermometer. You would have to have uncertainty from that. If your method requires you to have a specific time interval, you would use a stopwatch. How do you know your stopwatch is accurate? It's basically sitting back and thinking, I have to use A, B, and C. How do I know that they are accurate? If you know that there's a COA, you can prove that it's okay. A lot of the times what we do is all of us don't have every single thermometer in our laboratory is calibrated. Have a calibrated thermometer that goes away to a calibration facility and then verify the rest of your thermometers against that thermometer. Have that as documented procedure, have documented proof, and use that in your uncertainty as well. I hope that answers the question. Okay. The other question was about robustness, if I'm not mistaken.
Yes, robustness and sensitivity.
Robustness and sensitivity. So ideally what we want is we want to know, like I explained, an analyte or your instrument and your method are sensitive enough, for the lack of a better word, to still find that analyte when there are interferences. Robustness, we are often changing external environment, whereas interferences more than likely are interferences in your matrix. You can report the two of them together in certain instances. But there are instances in some very complex methods where you would have to then determine them separately. Also, rule of law, you don't want to change too many things at the same time. So if you are changing your analysts, then try and change only your analysts and not your balances and your instruments. If you want to change more than one, try and keep record of it. But when your method validation is really complex or your method itself is really complex, changing more than one sometimes makes it very difficult to prove sensitivity and robustness combined.
Okay. And the last question in that round was on regression uncertainty.
Hmm.
Yes.
So how do we determine regression uncertainty?
Yes. Yes.
Okay. Wonder if I should go back to my presentation and show that section. Perhaps I should do that. If we can just get back there. Regression uncertainty. Okay. So here we are. So what we are going to do is you are going to have your data, and I hope everyone can still see my screen. You're going to have your raw data and you're going to make your, basically this is an XY scatter to show that you are linear. You're going to use ANOVA if you use your Excel. And you don't have to be an Excel boffin, and you certainly don't have to be a stats boffin to be able to do this. ANOVA is built into your Excel. So you can then go and download it. It's usually an add-on package that you need for statistical analysis. You then go and you select ANOVA. So you basically click a block and say select ANOVA. And usually it's for single factor. And you then, this is what will get spitted, Excel will give you. A lot of this is usually to most of us. I started there too. But what we are looking at is these F critical factors. And then you're going to take that and let me see if I have it in mine. Uncertainty in sample, you'll see that I say that there was none there. I've then calculated the calculated versus the critical down here. You'll see it says 0.07 for organic matter. I'm taking that value out of my ANOVA value down at the bottom. Sorry, I'm really flexing through my slides now to show you, but I'm taking this value down here. Okay, good.
Right, thank you. I think that was clear. I think I have four more questions. I can just run through them and probably you just respond at once. The first one is on your fitment for purpose statement. Um, so obviously it would need some guidance to it in terms of the expected performance. Say for instance, your repeatability, is it supposed to be, if it's RSD, is it supposed to be 5% or is it 2%? How do you establish that for you to then have your statement of fitness? Then the other one is on the difference between linearity and working range. Um, I think you explained on the linear curve. I think the person is any difference between the two and what that difference is. And also if you can explain further on the difference between LOD and LOQ, and especially on how these are used. I think those are the questions that are currently there. Maybe I'll then put out, this is from me on Agromat, on the Agromat CRM. Please remember, just comment on that, where members can actually find that, because we have quite a number of requests on where laboratories can actually source CRMs. So we would want to expand that pool so that we may know where to refer laboratories. And I'm happy, I think this one you also responded to it, but let me just pause it as well on the use of the captured uh, errors on glassware, say for your microprepares, the plus or minus 0.005. I think you presented there when you want to establish the uncertainty for that, you would then need to put out the volume weight. Should you go that route, or you can just use what is on the glassware itself? I think that's the last set of questions, but I would encourage members to bring some if they are. We still have about 10 more minutes for the question and answer before we hear the closing remarks.
So to answer the Agromat question, I know the local supply or local distributor here, but SPC Science actually makes the standard. So I'm pretty sure if you just Google it, HPC Science will probably come up more than likely, if not your local distributor, but you then can probably get in touch with them and they would be able to tell you where to get it wherever you are in the world. I think that would be the best bet. I I don't really know where else to get it outside of here, to be honest with you. Then to touch on your question about uncertainty with your glassware, you can use the glassware uncertainty that's on your glassware itself. There's nothing wrong with that. I prefer to include it because for me that's just a more holistic approach. Often your glassware does not give you too much of a difference, so it's not necessarily going to interfere with your or increase your uncertainty in any way. You can do it either way. Honestly, it's just my preference is to include it in everything that I do. Okay. Then the other question was the difference between LOD and LOQ. So basically, LOD, limit of detection, is how low can we go that we can still see a result. We can still see a concentration of an analyte without the noise from our baseline actually interfering with us. So you'll see in the presentation that I had, the squiggly lines with the noise and a little peak on top. Sometimes that peak is only this big. Can you actually quantify that properly? Can you actually determine that, or would that peak be bigger? So what we do as a general rule is if that peak, whatever the analyte concentration, the absolute lowest you can get before you are in your baseline noise, you take that and you multiply it by 3. That's your LOD. So you have to essentially determine what is that absolute low and then multiply that value by 3. Your LOQ is limit of quantification. Once you've determined your LOD, you simply multiply that for your LOQ as well. So I'm going to go back to a particular, I should have left this open, a particular slide that I want to show you. I'm just going to scroll through here quickly. Okay, here we go. So you'll see here is what I'm talking about. That squiggly line down there that you see is just your baseline noise, and then there's that little blip that goes up there. If I zoom into that, this is what it actually looks like. So we determine what is the concentration of this little peak that you see, and we multiply that by 10. That gives us our LOD. It sounds quite easy, but it does take a bit of work. And then what you want for your LOQ is a signal to noise ratio of 10. That's all we need to do. So you take the concentration of your analyte, that gives you a signal to noise of 10. That's how you determine that. You will see here that the peak is much, much higher on an LOQ than it is on an LOD. So you would really need to have an analyst that is able to interpret what they're looking at when they are working on their ICPs, for instance. This is on ICP, it's one of the more complicated ones. Does that answer the question? Do I need to explain it a little further?
I think you addressed it on that
Okay.
list of questions. I think the only one left is on the fitment for purpose statement. How to establish those.
How to establish that?
Yes.
Okay. I'm going to scroll all the way back to the beginning, and basically your fitment, your statement's going to determine. I'm going to go even further back while we're talking about this, and we are going to say we need to provide objective evidence that the given item fulfills specified requirements. That is actually out of the ISO 17025. So what we need to do is we want to say the fit for purpose is when the method is performed, is it actually within the boundaries that we are specifying? That's the key factor there. So I'm going to go through this very quickly again and take you back to the slide that the validation plan one here. So what you can do for your fit for purpose is ask yourself these questions. What is being determined and why are we determining it? What's your matrix? What are your possible influences? You may or may not always have that answer. If it's something like fertilizers or animal feed or human feed, are there any legal requirements that you have to take into account? Heavy metals, for instance, there is a specific table 12 in Act 36 that you have to look at. You cannot go over a certain concentration of heavy metals. Take that into consideration here for legal requirements. How robust must the method be? Must I be able to do it when it's 40 degrees outside and my air conditioners are struggling a little bit indoors to keep my lab at 21? And must I still be able to do it when it's minus 10 outside and my air conditioners are struggling to keep my lab warm at 21? So those, you need to understand your environment a little bit as well. Expected concentration levels. So, you know you can determine carbon at 5%, but can you determine carbon at 0.01%? Is it even feasible in your laboratory with the instrumentation that you have? I've touched on environmental conditions again, and then the kind of instrumentation. So if you're doing heavy metal analysis, are you using an ICP OES or using an IMET? The difference in those instrumentations and the way you're going to get those results will also influence this. And then obviously, if you do sample preparation and subsampling, are you covered by a method? Do you actually comply to all of those requirements? Those are separate requirements to what an analytical laboratory does. So your fit for purpose statement is basically going to incorporate all of this and try and be, it's a fine line, be as summarized as possible, but be as detailed as possible as well. And then so that at the end, you can simply say this method is fit for purpose. To say, we are trying to determine calcium, magnesium, potassium, sodium, sulfur in sandy soils between the established working range kind of thing. And that's going to be your statement. I hope that answers the question.
Yes, pretty much well. I think it leaves me to thank you so much because of time. Unfortunately, we'll not be taking more questions, but Noorunisha shared her contacts. I think if you go onto the Glossaland webpage, they are also there on where we actually publish this webinar. You can actually have them there. I think let me just address the two questions that are coming up mostly from the listeners. The first one is on the slides. Like Norina said, I think you would notice her slides had a lot of animations. So she would try to clean them up for me and then she'll put them into a PDF. We'll actually upload them on the Glossaland webpage and we'll advise you once that is done so that you can quickly access them. Then secondly, this webinar will also be published there. Our comms team will work on it and then we'll also advise you when it is online. Then the other question is on the PTs. We've got two PTs and I think we had apologized on the AFRILAB PT results that have not yet been distributed to laboratories. But I'm happy to announce that the results are now ready. They are being finalized in terms of checking off and all the reviews. And all laboratories that participated in the AFRILAB PT for 2024 should be able to receive their results. Then secondly, we have a PT that just launched for the global PT. And I think members are also asking on the status of that. Again, the lab selection was ongoing within the Glossaland Secretariat. That has just been completed. So you may understand that the PT is just for 250 labs. Glossaland currently has in excess of 1,200 labs globally. So a selection process was done. Quite a number of AFRILabs were selected. So all the labs that were selected will be notified, and those that were not successful will also be notified. After which, sample distribution will then start and will be told of the next steps after that. And lastly, before I give over to Lesero for any closing remarks, we have a French version of this webinar, which will be presented by Ralph and Mustafa. So we'll also advise you on the specific date for that webinar. Those of you who would want a refresher specifically on this, we'll certainly have another one which will be in French specifically on the same topic. Before I hand over to Lesego, I don't know the other panelists if you have any remarks, Joseph, Rolf. Okay, nothing from Rolf.
Hello. Yeah, not much. Just to appreciate Ursula for making this opportunity available. We cannot underestimate the importance of this in trying to improve the quality of analysis in Africa. And thanks, Noorunisha, for a well done job.
Thank you very much.
Thank you.
And thank you to Bellington for affording me this opportunity as well.
Great. Thank you so much, Joseph and Noorunisha. And let me hand over this time to Lesego just for the final closing remarks. Lesego, please.
Lesego, you muted.
Yeah. Thank you
Okay,
very
thank
much,
you.
Bellington. It's been really a pleasure having everybody here. And we cannot go without saying thank you in a special way to Noorunisha Abdullah and Joseph Uponi. You really have done us a good favor. You may think it wasn't much, but please note that we really appreciate, and we have learned a lot, and we appreciate that you took your time. You volunteered your time. You volunteered everything. You gave it all to us. This time that we have spent here, it has been really of great value. And we're really, really thankful to you and to participants. It wouldn't have happened if you're not here. We really appreciate your presence, and the questions that you have shared were very, very important, not only to yourselves, but also to the panelists here, because it will help us either improve in a way or bring any change that we can bring to get these webinars even more productive than today. I thank you, everybody, and have a blessed afternoon. Thank you.
Thank you so much, Lesego. I think this brings us to the end of our webinar. Let me also thank you, Lesego, for all the efforts and the guidance. And thank you also, everyone, for joining through. We'll certainly meet in the next webinar. The next one will be in French on the same topic, and we'll advise you on the upcoming webinars under the AFRILAB. Thank you so much, and it's bye-bye for now.